Hello, I'm Tony Mann from the University of Greenwich, and I'm going to talk about some curious puzzles in decision mathematics. And first of all, I'd like to thank the organisers for inviting me to take part in this workshop. I've attended several of these History of Mathematics events at Birkbeck over the last few years. They've been wonderful events, and it's a privilege to be able to take part in this one. I'm talking about puzzles, and I think it's appropriate because one of the big ideas in decision mathematics came from Euler and came from his solution in 1736 of the problem of the bridges of Königsberg. Königsberg, a city in East Prussia on a river, and as we can see here, a river runs through the city, dividing it into several islands. There are 7 bridges connecting the various land masses. And the question was, the puzzle, is it possible to go for a walk through Königsberg, crossing every bridge exactly once, not using any bridge twice, and returning to your starting point? And this is the famous problem which Euler solved and initiated a whole new area of mathematics. I'm going to try, where possible, to avoid spoiling puzzles in this talk by giving solutions. So if you don't know the answer to this one, you might like to think about it. It's a beautiful piece of mathematics. So I'm going to discuss in this talk 4 problems, puzzles. The first is a secondary problem. The second is a variation called comparing 2 numbers. Third is the well-known Gale-Shapley algorithm for matching 2 sets. And the fourth is the Sleeping Beauty problem. And what I want to look at is what these puzzles tell us about mathematics and its connections with the real world. I'm interpreting decision mathematics here fairly loosely. I'm sorry if you think these algorithms don't relate to decision mathematics, but I think it's arguable that they do. When I got my first job after graduating, I was working for an engineering company, and one of my colleagues had written a program to advise which power plant should be on stream generating electricity at a particular time. And he was frustrated because he couldn't prove that his algorithm was effective. And this was because when the algorithm told the engineers to do what they were planning to do anyway, well, they did it because they were going to do it anyway. If the algorithm suggested something other than what they were going to do, then they would argue that for operational reasons, their method was better, and they wouldn't carry out the algorithm's suggestion, and therefore it wasn't possible to get evidence. And this relationship between mathematics and the real world has fascinated me ever since. Anyway, the first problem I want to discuss is the so-called secondary problem. So this is a problem in the field of optimal stopping. And in one formulation, this one is taken from Wikipedia. Here's the situation. We are interviewing or seeking a new secretary. There are n applications where n is a number known in advance. We can, once we've seen the applicants, we can rank them in order, unambiguously, no ties. We will see the applicants in a random order. We don't know whether the best one is going to be first or whatever. But once we've seen an applicant, we must immediately either accept them or reject them. We can't go back to a previous applicant, and if we accept an applicant, that's the end of the process, and we don't look at the remainder. And the decision can only be based on relative ranks of the candidates seen so far. We don't know how the future ones will fit in. So that's the problem. And there is a solution to it. But the objective, first of all, is to maximize the probability of selecting the best applicant. That's the only objective. If you don't get the best applicant, we don't care. how good or bad the applicant viewpoint is. The question is simply, what is the way to maximize the probability that the very best applicant will be selected by this process? And I'd like to just mention a fascinating talk on this topic by Nigel White at a BSHM Christmas meeting in Birmingham some years ago. I think it was probably 2012, but I'm afraid I haven't currently got access to my office, so I haven't been able to check my BSHM bulletins to check the date. So where did this problem come from? It was first published by the great mathematical popular writer Martin Gardner in his Mathematical Games column in Scientific American in 1960. He published it as a problem called The Game of Google, but the problem had been around for some time before that in the maths community. Merrill Flood had presented a version which he called the fiancé problem in 1950, and for full details, there's a paper by Thomas Ferguson called Who Solved the Secretary Problem from 1989, which is freely available online, which I recommend for the background to this problem. And the problem has a solution. The solution is that you reject the first n over e applications, where e is Euler's number, Euler again, Euler's number, the base of natural logarithms. So we reject the first n over e applicants. Obviously, n over e is not an integer, but the integer closest to that. And then we accept the first of the remaining candidates who is better than any of the previous applicants. And this gives us a probability of choosing the best applicant of at least 1 over e, or about 37%. And most people think, if they haven't seen the answer before, that is surprisingly high. And so it's a very effective algorithm. It gives us almost a 40% chance of selecting the best candidate. Martin Gardner credits Leo Moser and J.R. Pounder for the analysis of this problem, but there's more discussion in the paper by Ferguson that I mentioned earlier. Here's how Martin Gardner presented the problem. He called it the game of Google. Ask someone to take as many slips of paper as he pleases, and in each slip, write a different positive number. The numbers may range from small fractions of 1 to a number the size of a Google, 1 followed by 100 zeros, or even larger. The slips are turned face down and shuffled over the top of the table. One at a time, you turn the slips face up. The aim is to stop turning when you come to the number that you guess to be the largest of the series. You cannot go back and pick up a previously turned slip, and if you turn over all the slips, then you must pick the last one turned. And that is essentially the same as the secretary problem previously described. Gardner does give another formulation. He says the game has many interesting applications. For example, a girl decides to marry before the end of the year. She estimates she will meet 10 men who can be persuaded to propose, but once she's rejected a proposal, the man will not try again. What strategy should she follow to maximize her chances of accepting the top man of the 10, and what is the probability that she will succeed? And that's probably fairly light-hearted suggestion by Martin Gardner, and certainly rather dated in its context, but it does give another variation on this problem. So there are earlier versions of the problem. Arthur Cayley gave an example. Arthur Cayley, this old photograph, PowerPoint helpfully suggests this is a photo of a person in a suit talking on the phone, which I rather like. Anyway, Cayley proposed a problem in 1875 in the Educational Times. A lottery is arranged as follows. There are n tickets representing A, B, C, etc. pounds respectively. A person draws once, looks at his ticket, and if he pleases, draws again, out of the remaining n-1 tickets. And so on, drawing not more than k times, and he receives the value of the last ticket drawn. Supposing that he regulates his drawings in a manner most advantageous, what is the value of his expectation? I notice this is a rather different problem, because instead of trying to maximize the chance of drawing the top ticket, we're trying to maximize the expected value, which is rather different and probably actually more practical. Another early example, and is Kepler. We used this procedure or a similar procedure to choose a wife in the early 17th century. When Kepler's first wife died, he investigated 11 candidates for a second wife. He interviewed them all. His preference initially was for the fifth one, but after consulting his friends and family, they recommended for financial reasons he go for the fourth. So he went to the fourth candidate, but she rejected him, and he then settled for the fifth candidate and had, as far as we know, a happy marriage and successful marriage to her. But notice this isn't really the secretary problem as described, because he interviewed all the candidates before making a decision. So what does this problem mean? It's a nice piece of mathematics. It gives us a nice answer to a mathematical question. What does it tell us about real life? When do we find ourselves in this position in the real world? Well, one example might be driving down a motorway when you have to refill your petrol tank. You have a limited number of options because there will be limited service stations coming up. You probably know how many there are, but you don't know what prices they'll be charging. How do you choose which one will give you the cheapest fuel? And studies suggest that people in these situations tend to stop too soon. But is that because they don't know the mathematics, or they don't believe in mathematics? Or is it perhaps because the mathematics doesn't capture the whole situation? Perhaps for many people, driving down a motorway is worth paying a little more to reduce stress, to avoid having to think about the problem for a foreseeable period of time. So, does mathematics solve a problem for us, or does it solve a slightly different problem and fail to capture the whole reality of the real life situation? And the other question is, do we ever want the optimal solution? I mean, we obviously do want the optimal solution, but do we want only the optimal solution, or would we rather have a very good one, especially if there's risk of getting a less good one by trying to get the optimal? I mean, in the secretary problem, if the best candidate happens to be one of the first 37%, we will reject them and then end up with the last candidate of all who may not be very good. Is that a good outcome? Another question is, what happens if the other party is using the same principle? To take Martin Gardner's example, if I decide to reject my first 37% of my potential spouses and then take the next good one comes along, what happens if they're playing the same game and I happen to be one of their 37%? Then they will reject me. And so the interaction between two people using the same idea is going to cause difficulties in this method. So do people use this for selecting secretaries or other appointments? It's not very fair. The first 37% of the people you interview will not be selected. So that's not a very fair method. It's not going to be particularly satisfactory. The chance of getting the best candidate is only 37%. And if you don't get the best candidate, you may well get one who is not nearly so good. So this is not good recruitment practice. And thankfully, most companies do not recruit in this way. So that was the secretary problem, but I want now to look at a version, a cut down version called comparing two numbers. And this one comes from Peter Winkler's recent book of mathematical puzzles, published earlier this year. This is a wonderful book of fascinating and often deep mathematical puzzles which I cannot recommend too highly. And the comparing two numbers puzzle comes from this book, but it's essentially the first of a cut-down version of the game of Google that Martin Gardner proposed. Martin Gardner wrote that when there are only two slips, the chance of winning is obviously 1/2, regardless of which slip you pick. So to demonstrate this game, I've asked my recent maths graduate, Ruth, to play the game with me. I've written on two cards, two numbers, possibly negative. Ruth can pick one of the cards and can see what's on it, and she can then choose whether to accept that or take the unseen one. So what is Ruth's best strategy in this game? And what is her chance of winning? Well, here's the game. So Ruth, I'm going to show you two cards here, one in each hand. There's a number on the back of each card, and your aim is to choose the bigger of the two numbers. So you can choose which one you want to see, and I'll show you that one, and then you can decide whether to keep that one or whether to change. So do you want the one in my left hand, which is this one, or in my right hand, which is this one?
I'd like the one at the left.
Right. Well, the one in the left hand is number 73. Can you see that?
Yes,
So
I
now,
can.
do you want to keep that one, or do you want to change to the other number, which might be bigger than 73 or less than 73?
I want to keep that one.
And you're right, because the other number was 72. So well done.
Thank you.
So Ruth won the game, but did she use the optimal strategy? Can you find a strategy which has a better than 50% chance of winning? Gardner said that when there are only two slips, your chance of winning is obviously 1/2, regardless of which slip you pick. And that statement, I think, is correct. Nevertheless, it is not obvious. In fact, it's, I think, extremely surprising, but your chance of winning with the right strategy can be greater than 1/2. And the puzzle is, what strategy can you devise which gives you a greater than 50% chance of winning this game? And I think it's quite remarkable that is such a strategy. Okay, here's version 2 of this puzzle. This time, the two cards contain a random number. I've used Excel to generate these numbers. A random number between 0 and 1. Ruth will look at one and then can choose whether to accept the other or take the one she's seen. And what's her best strategy? In this case, she knows the two numbers are random, so she has a strategy which is actually much better than choosing randomly. And I'll leave you to think about what that strategy is and move on to version 3. Again, each card has a random number between 0 and 1, and I've used Excel to generate these, so they really are, for practical purposes, random. I'm going to look at them, and I will choose which one of the two to show to Ruth. Ruth can then choose whether to accept that one or to take the one she hasn't seen. Now, if she chooses randomly, she has a 50% chance of picking the higher number. Can I make sure that her chances are no more than 50% by choosing the card to show her in such a way as to limit her chances to that? What's my best strategy for choosing which card to show her? I'll now play the game with Ruth, and you can think about what strategy I might be using. I've got two cards, and this time one is blue, they're blue backs, and they both have numbers. Numbers are between 0 and 1, and this time they were generated randomly. I used the random number function in Excel, so I've had no input, but I'm going to choose one of these numbers to show you, and I'm going to show you this one, which is 0.598. Do you want to keep that number, or do you think the other number might be bigger?
Okay. 0.598. Right. I think I'm keeping this again.
And you've won again because the other number was 0.365.
Yes. Okay. Awesome. That was fun. Thank you, Tony.
So Ruth won again. She said she was using a strategy of using my eye movement to try to decide which card was the higher. That strategy clearly worked in this case, but in fact, did she have a better than 50% chance of being successful? Or was she just lucky? Did my strategy cut her chances to 50%? It did, barring psychology and eye movement analysis. But what was that strategy? Again, it's quite interesting that such a strategy exists, and I leave it for you to think about. My next example is the Gale-Shapley algorithm. This is an algorithm used to pair off sets. We have two finite sets, A and B, of equal size, and we wish to pair off the members of two sets according to their preferences. Each member of both sets has ranked all the members of the opposite set in their order of preference. We're going to pair them off. How can we do this to provide the best outcome? But what is the best outcome? We can't guarantee everybody their first choice, because two members of set A might choose the same member of set B as their first choice, and they can't both be paired with that member. But it turns out we can guarantee a stable matching in which no pair, A from set A and B from set B, prefer each other to the matches assigned by the algorithm. And that is quite useful because, as the name suggests, such a matching stable. You don't risk A and B abandoning their partners and joining up in a couple to, despite what the algorithm says. In fact, if an algorithm doesn't produce a stable matching, the matching is unlikely to be very effective. And it turns out the Gale-Shapley algorithm finds an optimal stable matching. It's named after David Gale. PowerPoint didn't suggest anything very interesting for this photograph. And Lloyd Shapley. And Shapley won the Nobel Prize for Economics in 2012, which just shows how important this kind of decision mathematics can be. So here's the Gale-Shapley algorithm. The members of set A, or as you prefer, set B, sit at tables, 1 to each table, and a number of rounds take place. Initially, everybody's unpaired. So initially, all the current members of set B, or in subsequent rounds, all the unpaired members of set B go to the table of the partner they most prefer who has not already rejected them. Initially, nobody's been rejected. So in the first round, everybody in set B goes to the table of their top choice in set A. Members of set A may now have nobody at their table, in which case they have to wait. They might have exactly one person, so they keep them at that table, or they might have several people, in which case they choose the highest ranked of the people at their table and reject the rest. As a result of this process, some members of set B will be rejected, so they then go back, and then round 2 begins, and the same thing happens again, with all the currently unpaired people going to another table. And this process will continue. When this happens, one of the members of set A, who had previously accepted somebody, might then reject that person in favor of a better partner who comes along. The process continues, and it will eventually terminate, and when it terminates, all the couples are paired off, and this is a stable matching. And all of that is quite easy to prove. And as I said, this is optimal in the sense it finds the optimal pairings for similar members of set B. Obviously, not everybody gets the first choice, but it's optimal in the sense that there's no other matching, no other stable matching in which the members of set B, in which any member of set B is assigned a partner they prefer the one allocated by this method. So every member of set B gets the best possible partner they can have in any stable matching. So that looks pretty good. However, it's not quite so good for members of set A. They in fact get the lowest ranked of all the partners they can have in any stable matching. The worst possible pairing for members of set A. And so what this shows is that the choice of which members sit at the tables and which members move around the tables is quite critical, and you will get different outcomes, and which is your priority. So this shows us, for example, the choice of algorithms is political. Do you favour set A or set B? Which one do you arrange to have the best outcomes? This algorithm has been used for assigning medical trainees to hospitals. In fact, an algorithm like this was in use before Gale and Shapley devised this algorithm. Trainee doctors, hospitals will prefer particular trainees, particular specialities. Trainees will prefer particular hospitals for travel reasons or whatever. So do you use the algorithm to be optimal for trainees or for the hospital? You get different outcomes. Which one gets priority? And it's tempting, and I've tried to avoid doing so far, but lots of lecture presentations of the algorithm on the web present the algorithm in terms of dating, of pairing off heterosexual couples. And I think this is quite an entertaining caricature. Some of the lectures use the ideas behind the algorithm to discuss whether particular dating cultures favour men or favour women. They argue that cultures in which women are active in choosing partners lead to better outcomes for women than when they're more passive. But is this meaningful? Is this useful? Is the real world like this? In dating, people change their opinions. There's no single ranking of all your possible partners in order which isn't likely to change over time as you get to know people better. So the conditions of the algorithm won't really apply. Can we come to any meaningful conclusions? Does the algorithm tell us anything meaningful about the world? I'm not sure. It's a very useful algorithm in certain situations, but I think it's dangerous to extrapolate, to draw out conclusions about how the world behaves from the mathematics. So what I love about this algorithm, apart from being a nice algorithm and simple to use and of real world importance, is it provides an excellent example in teaching to raise awareness around the issues around using mathematics in the real world. There's circumstances in which the algorithm applies, the choices you have to make in applying the algorithm are all, I think, important lessons for people applying decision mathematics in the real world. I'm now going to move on to the final puzzle I intend to discuss, the Sleeping Beauty problem. This is a famous puzzle, which I'm afraid I only came across earlier this year in a talk by Peter Winkler. He was giving an online talk at the Museum of Mathematics in New York. I was watching in bed because of the time difference. Peter Winkler finished his talk with this problem, and it kept me awake all night. As it happened, a couple of days later, I was at a conference at which a student talked about a similar question. I told him this problem, and he told me it kept him awake all night too. So apologies if it does the same to you. This puzzle was created by Arnold Zunoff in the 1980s and seems to have been first published by Adam Elga in 2000, and it's discussed by Peter Winkler in the book I mentioned earlier. So here's the scenario. An experimental subject we will call Sleeping Beauty is put to sleep, and she sleeps from Sunday until Wednesday with the interruptions we'll mention. After she has gone to sleep, a fair coin is tossed. If the coin is heads, Sleeping Beauty will be woken up once on Monday and otherwise undisturbed until Wednesday. If the coin is tails, she will be woken up once on Monday and also once on Tuesday, and then again will sleep till Wednesday. When she's woken on Monday or Tuesday, she isn't told what day it is, and she won't remember any of her previous awakenings. So that's the slightly unlikely scenario. The question is, Sleeping Beauty knows the full protocol. She knows all these arrangements. When she's woken up during the experiment on either Monday or Tuesday, what should she think is the probability that the coin came up heads? What's her best estimate for the probability that the coin came up heads? Okay, I'm going to give two arguments for solving this problem. Here is argument one. There are four possible events of interest. The coin could have come up heads, it could be Monday, and Sleeping Beauty has been awakened. It could have been heads, and it could be Tuesday, in which case Sleeping Beauty has not been awakened. The coin could have been tails, it is Monday, and Sleeping Beauty is awakened, or it was tails, it is Tuesday, and Sleeping Beauty is awakened. And each of these initially is equally likely. So, suppose Sleeping Beauty is awake, then it cannot be Tuesday and the coin heads, because Sleeping Beauty wouldn't be awake on a Tuesday if the coin was heads. So that leaves three possibilities, they're equally likely. Therefore, the probability the coin was heads is 1 in 3, because in 2 of the 3 events, the coin came up tails. So that's the argument, and that shows the probability is 1/3 from Sleeping Beauty's point of view. Here is the second argument. When Sleeping Beauty was put to sleep on Sunday, she knew that the coin toss would be fair, and the probability the coin would be heads was a half at that point. When she's woken up, she has no new information. She knew she was going to be woken up. So when she's woken up, that doesn't tell her anything. So she must still think the probability of heads is 1/2. So these are two convincing arguments, and the only problem is they give different answers. The question then is, are you a thirder or a halfer? And it turns out that over 100 papers have been written in philosophy journals on this question. So this appears not to be a very simple problem. So apologies if this keeps you awake all night. What does this puzzle tell us? It tells us, I think, that decision science, and particularly analysis of probabilities, can be difficult. And even academic philosophers sometimes get it wrong. So to conclude, we've looked at some interesting puzzles. I hope that I've tried to persuade you that puzzles are fun, but they can actually help us clarify our thinking in decision mathematics. And they can also lead us to think about the relevance of the puzzle, and indeed the relevance of the mathematics to the real world. And I think this is, it is important as mathematicians to be aware of the limitations of mathematics as well as its power. My thanks again to the organisers of this meeting for the invitation, and to Ruth Ejigayehu for taking part in the recordings of the game. So thank you very much for watching.